That was me at Kennedy Space Center in Florida, where I was invited for the International Space Settlement Design Competition earlier this year. It's a competition where we designed futuristic space settlements, for example, a lunar mining outpost set in the year 2055. But in order to ever build one of these awesome ideas, we need a way to reliably get stuff from Earth into space and vice versa. And in this video, I'm going to show you some of the maths and physics behind how that works. Don't worry if that sounds scary, I'm only going to use stuff you would have learned in high school. But before we get there, we do need to think about paying for all of this, because space launch costs are astronomically high, and we need a way of bringing that down if we ever want to build something like this. And we're already getting there. The cost per kilogram to low Earth orbit has come down drastically in recent years, thanks to the likes of SpaceX's Falcon 9 rocket. But why only in recent years? To understand why no one was focused on building self-landing, fully reusable rockets until now, we need to look at how the space industry's priorities have changed over time. In the 50s and 60s, the US and USSR's priorities was to get to space in the first place, and then the moon. No one was focused on how to repeat such a feat. It was about being the first to get there. And that meant we threw a lot of stuff away, including the entire rocket that Neil and Buzz launched on, the Saturn V. Only the very tip of that rocket came back to Earth, and some of it even burnt up on re-entry. As time went on though, NASA did get better at reusing bits and pieces of its launch vehicles, and this was in part due to increased political pressure. Spaceflight was very expensive, and this meant that tax dollars had previously been spent on rocket engines that were used once then burnt up in the atmosphere or were relegated to the bottom of the ocean. Well, until Jeff Bezos pulled one up, that is. Whilst the space shuttle was an improvement, NASA's bureaucratic nature had meant that they moved slowly. By the time the space shuttle launched, after years-long pushback and delay, technology had advanced so much that it was already somewhat outdated. It cost billions to refurbish, took years to do so, and was only partially reusable. It wasn't exactly the cost-saving vehicle it was envisioned to be. In NASA's defense, it was during the mid to late 1900s that humanity pioneered this technology in the first place. They had to turn classical physics into real engineering to achieve human spaceflight. Someone had to walk so that others could run. The private space sector has exploded over the past 20 years, with one kingpin that may come to mind when I say the words self-landing rocket. That's right, SpaceX, who have been able to reliably land their Falcon 9 for almost 10 years. Well, 97% of the time, at least. You may see this and think, why? When you've had all that time falling through the atmosphere, would you only slow down right at the end when you're about to smash into the ground? Because instinctively it may seem like you're giving yourself more work to do by letting the rocket speed up so much as it falls through the atmosphere. But in fact, slowing down in the atmosphere would mean more time spent opposing gravity, and so the less fuel efficient your rocket would become. So only relighting at the very last second possible is the most fuel efficient, energy efficient way of doing things. And it's called the hover slam. Okay, so how does the rocket know exactly when that very last second is? Well, the answer's not as complicated as you might think.
When something falls, a pen, your phone, a rocket, it's not just moving quickly, it has kinetic energy. To stop our falling object, we need to bring its kinetic energy to zero. You probably remember that kinetic energy, EK, equals a half mv squared from school. But don't worry if you don't. The important bit is knowing that going faster means more kinetic energy. We can simplify this a little bit by talking about the kinetic energy per kilogram of the rocket. So the falling rocket has a half v squared of kinetic energy per kilogram. EK equals a half v squared.
For rockets like SpaceX's Falcon 9 or Blue Origin's New Glenn, the only tool they have to cancel out all this kinetic energy and therefore slow down is the engine. And to do this, they need to create an upward acceleration. But this acceleration doesn't just act against the rocket's downward motion, it's also defying gravity.
So, we can define the rocket's overall upward acceleration as A equals nt minus g, where n is the throttle between 0 and 1, t is the engine's acceleration at full power, and g is the acceleration due to gravity. When the rocket fires its engines again, It's doing work, which you may have learned as work done equals force times distance. But if we measure work done per kilogram, we can divide through by mass. And thanks to F equals ma, our force, when divided by mass, becomes acceleration. So we end up with the work done per kilogram equaling acceleration times distance. Meaning we have an equation for the amount of energy that the rocket engines use in terms of the rocket's acceleration and the height it falls during that acceleration. Now, watch what happens when we set our two equations equal to each other. We get a master equation.
You may be thinking, great, but how does this get us any closer to finding when we need to turn our engines back on? Well, all we need to do is rearrange our equation to make h, or height, the subject.
This tells us that if the rocket is falling downward at speed v, and the engines can generate this much upward acceleration for a given throttle n, then our rocket needs to be exactly h meters off of the ground to slow down and land safely.
So as the rocket is falling, its computer is constantly checking what's my altitude, what's my height, to work out if realizing its engines at that point would stop it in time. And when the actual measured height of the rocket matches the computer's calculated height, ignition. But real life is messy. There's wind, air resistance, fuel burning off, changes to the rocket's angle, and even changes in the gravitational field strength. So once the engine is back on, the rocket keeps constantly adjusting the throttle value n.
To work out what that value of n should be, we once again rearrange our equation from earlier to make n the subject instead of h. This makes it so that if the rocket starts slowing down too soon, n should decrease, throttling the engine down. And if the rocket is still falling too fast, n increases, throttling the engine up. This process happens dozens of times per second to make sure the rocket safely touches down.
And that's how rockets land the way they do. Watching a multi-story building bring itself to a gentle rest on a ship floating in the middle of the ocean can look a bit like magic. But behind the scenes, and with some oversimplification, we can break it down into kinetic energy, acceleration, work done, and a bit of rearranging. Alright, we've seen how rockets land, but that still begs the question, why did it take so long for us to get here? Because none of the physics we've explored in this video has really changed since Isaac Newton discovered gravity. We didn't need to reinvent maths to do this. What held us back was turning our theory into reality. We now have rocket engines that can precisely throttle without exploding, computers and sensors fast enough to update hundreds of times per second, and materials that can survive re-entry again and again. But most importantly, we had a reason to try. For decades, rockets were government hardware and tools for winning geopolitical goals. Once private companies entered the game, the economic advantage of reusability became obvious. If we can reuse one rocket 10 or 20 times, you don't need to build 10 or 20 rockets. And to me, that's the real story here. Humanity stopped treating rockets like single-use disposable fireworks, and instead like aircraft, something designed to fly again, to come home. And if we can do that with one of the most extreme technologies that humanity has ever built, where else could it happen? A future where we reuse more, waste less, and design with intention won't all arrive at once. It arrives the same way these rockets land, one careful adjustment at a time, with new ideas tested, refined, and corrected. Anyone who follows this could take something previously impossible and make it suddenly normal. In fact, the maths we've done in this video shows just that, and it's why I've just bought this. And in an upcoming video, I'm gonna try and code it to land like a rocket following the maths we've explored in this video. Next time you see something that blows you away, remember that it might not be as out of reach as you think. If you're also inspired by tools, technologies, and people making an impact on our world, stick around. I have been JaggerCD, and this was Earth Catalogued.